In this lecture we talk about a path in space X. So path in space X is a map. So essentially path looks like this. So say this is some space capital X. So the path from X to Y in this space X looks like this. But a more formal definition is that it is just a mapping. So you start with a unit interval 0 to 1 and you map this unit interval into the space X via this map U, such that the 0 gets mapped to X, this 1 gets mapped to Y, and the straight line becomes this squiggly line in the space X. So U of 0 is X and U of 1 is Y. So U is a path from X to Y, and you write it like this: U is a path X squiggly to Y. So essentially what we are doing is we are taking this unit interval and then we are somehow stretching it and bending it to get a path. Now if X is equal to Y, then we have a loop. So if X is equal to Y, then 0 and 1 get mapped to the same point and you get a loop. So this is at point X. So we can talk about loop. Now we have defined the paths, we can define equivalence relation on paths. So for equivalence relations you need three things. You need transitivity, you need symmetry, and you need reflexivity. So first we will talk about transitivity. So say we are given two paths U and V. So U goes from X to Y. So say this is the path U. And then you have path V which goes from Y to Z. So say you have path V. So now we can concatenate these two paths. So notice that our T has to go from 0 to 1. So this variable from 0 to 1 is say denoted by T. So this T has to go from 0 to 1 for either of the paths. So what we will do is a total T has to go from 0 to 1. So you make sure that you travel from X to Y in till half T, and then from Y to Z in another second half of T. So total is 0 to 1, because this you can see is unit interval 0 to 1. So obviously to come to this part you just clear the denominators and then you will have 2t here. So you clear the denominators, you will have 0 less than equal to 2t less than equal to 1. So again, if you normalize to 0 and 1 you get 2t, and this is precisely what goes in here. Similarly here, if you normalize this, you multiply both sides by t, you get 2t less than equal to 2. Then you subtract 1 from all the sides, you get 2t less than 2t minus 1 less than equal to 1. So again normalize between 0 and 1, and this is precisely what is carried here. So this is important. Once this interval is given to you, you just need to focus on this interval, and when you normalize it between 0 and 1, you get this inside term. So these inside terms essentially come from the interval by normalizing it between 0 and 1. So we are not going to talk about these inside terms because these are automatically coming from the interval. So notice that the function composition goes from right to left because it is like Arabic. It goes first here and then here. But here we concatenate from left to right. So first you go U and then V. So U and then V. So you're going from here to here. So this was our transitivity. So if X is connected to Y and Y is connected to Z, then X is connected to Z. So second thing is that we need symmetry. So if X is connected to Y via this path U, then Y is also connected to X but via the inverse path. So to go from X to Y, we go from 0 to 1 here. So 0 is getting mapped to X, 1 is getting mapped to Y. So when you're traveling here, you're traveling here. Now you travel in the opposite direction. If you travel in the opposite direction, you're going from 1 to 0. So now your path is like this, which you call U bar when you're traveling in the opposite direction, and that you define as the same path U but 1 minus t. So when t is 1, then this is 0, and so on. So you have a opposite. So you have our symmetry. And finally we have reflexivity. So path X is connected to itself just via constant path. So the time as goes from 0 to 1, you just sit here. you do nothing. You just keep on sitting here for the entire interval. As this goes from 0 to 1, you just keep sitting here. So you keep sitting here, and that is just the constant path, which we denote as Cx of t, because no matter what the value of t is, you just keep sitting at this red dot of x. So now, once we have this equivalence relation on paths, let us talk about homotopy of paths. So say two paths u and u prime are homotopic. You write u homotopic to u prime if they are homotopic relative to 0, 1. So relative to 0, 1 means that the endpoints are the same. So these three paths in green, in yellow, and this greenish blue, all of them are homotopic. We can draw further homotopic paths, and so on. So notice that this path doesn't need to be injective. It could also go like this and self-intersect. So now we want to prove a small proposition. So say u and v are two paths given space x. So you have this path u connecting x and y, and then you have this path v connecting y and z. So obviously u of 1 is where y is, and v of 0 is again where y is. So these paths have to be connected. Now if u is homotopic to u prime, this u is homotopic to u prime, and this v is homotopic to v prime, then if you concatenate, then u and v, this is homotopic to u prime concatenated with v prime. So notice that we are putting this green square dot for composition of paths. So we will prove this now. So if u is homotopic to u prime and v is homotopic to v prime, then you can construct some homotopy diagram like this. So this x is this x, this y is this y, this z is this z, and these top paths are u prime and v prime. This bottom is u and v. So this is a square, and this side is 0, 1 unit interval, and this bottom side is also 0 to 1 unit interval. So s is varying here, and say t is varying like this. So there are two coordinates here, s and t. So now we construct the homotopy. So the first homotopy HST is H1 2ST. So this s is varying as twice the rate as t, where s lies between 0 and half. So this homotopy, it starts from here to here, and this given like this. So obviously again you can see, you can put normalize this will become 0 less than equal to 2s less than equal to 1. So we are not varying t, so t we are keeping as such. And obviously the second part is half less than equal to s less than equal to 1. So second part is from here to here. So this is the second homotopy. Again you will normalize this, you will get 2s minus 1, t we are keeping as such. And this is the homotopy which is required, which is basically homotope uv to u prime composed with v prime. So first travel u, then travel v, is homotopic to first travel u prime and then travel v prime. And this is you can see from here. So if you put t as 0, then you are here. So then you first travel u and then travel v, and you travel in terms of s. You can see that there is only s traveling here. Then if t is 1, then you are here, then you are traveling u prime and then v prime. So this is it. If you put s as 0, then you are here, you're just at x right here. And then if you put t as 1, this s as 1, then you are here, and here now t is z. So that is it. So this gives you homotopy. So just make sure that you understand that this is what is giving you the correct definition. So this is just follows from the definition of homotopy. So the idea is, if you draw a figure like this, then this just drops out, because s is just going from here to here and then from here to here. So there are two portions. So first part s is going from here to here, and then s is going from here to here. That's what we have written here. And just clear the denominators, make sure everything lies between 0 and 1, then this drops out as we have just seen before. So now say you're given three paths, u, v, and w. So say you have x, y, z. So there are three paths. So let's go to z prime. And then we have three paths. So we have u, we have path v, and then we have this path w. So we want to prove this big result, which basically says that because we are traveling, this entire thing has to travel in the unit interval 0 to 1. So this entire thing has to travel from 0 to 1. So this bracket means that first half of the interval you travel uv, then the rest of half of the interval you travel w, is same as first you travel first half of the interval you travel u, and the rest v and w travel in the next half of the interval. So this is the same. So you travel this first half and then this entire thing in rest half of the interval, because total has to add up to 1, is same as if you travel these two paths u and v in first half and then this in this half. The second part is just the path u. So path u takes you from x to y. So proving this just means that you have to draw a square where this relationship holds, and then this homotopy will just drop out of it. So what do we mean by this? So here we need a green composition dot. So what we are trying to do is we travel this w in the second half of the interval. So half is right here, because this half we are traveling in w, and this u and v we are traveling in the first half. And that is pretty much it. So this is the first half of the interval, this is the second half of the interval, so this has to be the midpoint, so this is 1/4. For the second part, we are traveling u in the first half of the interval and this in the second half. So that is it. So this is 1/2 and this is the second half of the interval, so this is 1/4. So again, this is a square, 0 to 1 we are varying s here, 0 to 1 we are varying t here. So s starts from 0, goes to this line. So equation of this line is precisely this. So equation of this line is s equals to t plus 1 divided by 4. So just find out the equation of the line which passes through 1/4 and 1/2. Obviously you use appropriate coordinates. So this is 1/4, 0, this is 1/2, comma 1. So that is it. So till less than equal to, and you can easily check it. So you put t as 0, so you get 1/4, which is right here, and you put t as 1, you get 1/2. So now for the second portion, s is between because s is on this axis, so now s is going from here to here. So equation of this line is t plus 1/4. Equation of this line is s equals to t plus 2/4, which is right here. So s lies between this line and this line. Finally, the s goes from this line. The equation of this line is again s equals to t/4 to 1, which is right here. And now this obviously comes from here. You clear the denominators so that this entire equation lies between 0 and 1. So you will get 0 less than equal to 4s, which will be less than equal to t plus 1. So now you have to make it between 0 and 1, so you have no option but to divide by t plus 1. So again, make all these equations between 0 and 1, you will get these inside expressions. So this is what precisely goes in here. So similarly we will do for 2 and 3. So now we are focused on this equation, so we are just going to do this part. So this u is here, it travels the entire interval. Here you first half you travel u, and then you sit at the point y. So as we said before, we have this path going from x to y, and this is our path u we are talking about. So again, you know, s is varying from here to here between 0 and 1, and then t is varying from here to here. So again, s goes from 0 to this line, which is t plus 1/2. So the equation of this line, which is from half to 1, this line is s equals to t plus 1/2, which you can easily check. When t is 0 here, you get 1/2. When t is 1 here, you get 1 plus 1/2, which will give you 1. So that is it. And then the constant path is here, so it sits here. the second half. So you can see from here to here you have this homotopy. So now we come to this number 3 part. So that is, you travel u and then u bar, that is in the opposite direction. It is equivalent to just staying at point x. So homotopically equivalent. So this is point x, this is point y. So you can either stay all the time at point x, or you travel u and then come back u bar. So travel u, come back u bar is same as staying at point x. So whatever time you stay at point x, you make sure that you go and come back and stay here the same amount of time. So this will be clear from the homotopy what I'm trying to say. The only thing you have to notice is that whatever you do with u, you have to do with u bar in the opposite direction. So rather than working on the interval 0 to 1, we have to work on this interval 0 to half for u, and then do exactly the same thing for half to 1 for u bar. So this u bar has traveling in the opposite direction. So rather than normalizing from 0 to 1, we have to normalize from 0 to 1 half, and then do exactly the opposite thing for u bar. So these two are symmetric. So we have to fix one of them, the other should pop out. So this is how the diagram would look like. So u bar, and then this is the constant path cx. So this x you can think of as constant path. So again, this is connected here, but if you just move it just epsilon above, you can see that this is your constant path. You remain at the constant path this point for some time, then you start traveling u. So whatever you travel with u, you have to immediately come back with u bar, and then if any other time is remaining, you sit at point x. So that is what the diagram is. So equation of this line is s equals to t by 2. So this line is s equals to t by 2, and this line is s equals to 2 minus t by 2. So as you can see, this is symmetric. So you sit on this point x, which you can also call as cx. We are just writing x here for till t by 2, and then you are again sitting at x from here to here, 2 minus t by 2 to s less than equal to 1. Now from here to here you are traversing u. So this red line is half. So from here to here, so this line is t by 2. So from t by 2 to 1 half you are traversing u. So if you normalize this, as I said, you keep half as such, you do not touch this half part, you normalize just this part. So you have t by 2 less than equal to s less than equal to 1 half. We have 1 half here, so we are not going to touch this. So normalize this, so you will get this as 2t minus s less than equal to 1 half. So just making sure that you get a 0 here. So this 2t minus s is what goes in here. So as I said before, u bar is exactly the same behavior. So you put u bar also as 2s minus t, but we have seen this. You can convert u bar to u by replacing s with 1 minus s. So replace s with 1 minus s. So therefore you get 2 minus 2s. And that is what the homotopy is. So only thing you have to do is just draw this figure, get these things, and normalize just this thing. So notice that we are not normalizing this portion, precisely because this has to be opposite of this. Anyway, this figure you can see it goes from half, from this red line, to 2 minus t by 2, which is this line right here. So in some places, and including this lecture series, rather than drawing the diagram like this, you can transpose it. You can draw this diagram like this. So this bottom line comes here, and then this red line comes right here, and then you can have figure like this. Now you will do homotopy from this side to this side. So this side you can have u and u bar, and here you have the constant path. So here the constant path is top, you can have it on the side. But again, these equations will change accordingly. So depending upon the context, this thing will change. But that is it. So we have proven all these three things, which immediately give you the fundamental group.